Welcome to our Interpretable Machine Learning lecture. My name is Ben Bischel, and here in this session we'll talk a bit about what a generalized additive model is, how model-based boosting works with simple base learners, so we can use that to boost models in a component-wise fashion, and how we can then exploit the, again, generalized additive model structure of such a component-wise boosting model to interpret the model in terms of feature effects and in terms of feature importances. And I'll do that again, as for all of these models in this chapter here, pretty briefly. We'll not really go into details, but we want to give you a good summary of how what interpretable model classes are available to you, and especially for these component-wise boosting models. I hope at the end of this session you will agree that this might actually be a pretty nice compromise between a risk minimizing machine learning perspective, where you can get a reasonable, good predictive performance, but you can still interpret the model quite well, so you can understand its feature effects. So the effects that each feature has on the outcome, and you're not really restricted to a very constrained model class where all of these effects have to be linear, and you can also fit these models with respect to basically arbitrary loss functions. So I guess we have all already understood that linear models are not that great if features act on the outcome in a nonlinear fashion. So if you would take a look at this data situation here, I guess we can agree that maybe the underlying trend looks a bit like this, and then fitting a straight line to such a data set, either in this 1D case here or in a multivariate case, doesn't really make sense. Of course, there are certain workarounds that we can use in linear models or in general in GLMs. So we can do feature transformations, so we can, take the x of a feature or the log. We can use certain base functions. So we discussed that the linear model is not necessarily constrained to these, straight line models where features act on the outcome in a linear fashion, but rather these linear models behave linearly in their parameter vectors, right? But in order to model these nonlinear data situations, we then have to come up with, don't necessarily want to say manually constructed, but at least manually provided, manually selected base functions. We can also include higher order effects. We can categorize our features. So for example, we can create certain intervals for numerical features. So we can kind of bin values. We can maybe say we have an age variable and that's continuous, right? And if this is continuous, of course, then our linear model can only model something like this, effects like this, right? We can now take our age variable and we can categorize that, into young persons of medium age and then persons of more senior age, then use this categorical variable and then maybe have something which models like this, so in a more nonlinear fashion. Okay, this is very often done in either in applied linear models or applied logistic regression models. But all of this is substantial extra work. Here we want to take a look at two model classes which might work a bit more automatical in these scenarios. So what's the idea now of a GAM? So of a generalized additive model. So instead of modeling linear terms, theta j times xj, so a coefficient times a feature value, we now use flexible but univariate functions fj. So my pen is gone. Let me grab that again. So we model like this, okay? So this is not so be careful here. So this is a univariate function, right? So it's a function that only acts on the feature xj, and we also use the j here as an index in the f, to make that explicit. So in general, our GAM model would look like this, right? So it's, of course, an intercept, and then it's the univariate function that acts on x1. So in a certain sense, the effect function, the effect curve for x1, and then another one for x2, and another one until we have arrived at the last feature xp. And this still gives us an additive structure, which we can nicely exploit, but it also allows us to model nonlinear effects for individual features. And we will now not pre-specify these functions, fj, but we can learn them, and very often we learn them by using splines, which is a pretty flexible model class, right? So We can learn pretty much arbitrary structures with this as long as there are no interactions, right? So if you look at this, what we allow through that model class is nonlinear effects of a single feature on the outcome, but we do not allow interactions between, for example, feature x1 and feature x2. If we want that, we now again have to manually prescribe that to the model, or we have to do something more complicated. But this is one of the downsides of the GAM, that we don't get the learning of arbitrary interactions for free. But if we would allow that, we are now really going over to pretty much non-parametric ML models. And then the downside of that is that these models are usually not really interpretable, because one of the major problems of models not being interpretable is unconstrained interactions in the model class. Okay, so how does that work? Can we maybe take a look at an example? So here we again look at our favorite example data set, so the bike rental data, and we now fit a GAM model with smooth splines to 4 numeric features of this bike rental data set to arrive at a more flexible and better model fit than for the more constrained linear model. So here you can see our numerical features. So you can see that we are using the temperature variable, we are using the humidity variable, we are using the wind speed, and the days since 2011 feature. So basically, I don't know, kind of a timestamp variable, right? So we have these 4 guys here, and here you can see the fitted effect curves that we fitted by splines, for example, here on the temperature, okay? So this now allows us not such a neat and compact interpretation as in the linear model. There we had like a single coefficient, and we understood immediately through that single one number how temperature, for example, acts on the outcome. So if we increase temperature by 1 unit, we know how our number of rented bikes goes up or goes down. I guess for temperature it went up, because there's a positive correlation, I guess, between warm weather and high temperature and how many persons rent bikes. Well, you can see here, not completely. It's not really linear, right? So we would have modeled something like this with our normal linear model. But here we are now automatically constructing this feature effect curve through a spline. So this would be our f1 function, f1 of x1, if x1 would be the temperature. And we can now interpret this feature effect at the very least through visual inspection. Now, there's also this concept of effective degrees of freedom, which represents the complexity and the smoothness of our curves, and we can control that. And I don't want to go into these details here. And what I do want to say is that if we have such a model class like a GAM, right, with this additive structure, so I guess I'm going to be lazy and just writing this down for, well, I don't know, I can write this down for 4 features like here. So we'd have a structure like this. Maybe let me write down an intercept term here. Now we have that. We have a function for f2. Well, okay, I'm going to be lazy, so I'm just going to write it down for the first 2. This here is what we later, for other model classes, will compute in a model agnostic fashion, and then we'll call that a partial dependence split, okay? For such a GAM model, we directly model that, and we can directly read it off from the model without spending any extra amount of work. Okay, so this brings us to the last part of this session here, which is on model-based boosting. So this will be, I'll introduce this now in a quite cursory fashion, just like summarize the major pros and cons of this. So model-based boosting, it's not a particularly super complicated model class, but it assumes that you already have understood boosting and gradient boosting a bit. If you have done that, it's actually not hard to understand what model-based boosting, how model-based boosting works. So hopefully you know that already. If not, learn that and come back to this here. So how does boosting work? Boosting iteratively combines weak base learners to create a powerful ensemble. Okay, so usually this works in a greedy fashion. So in every iteration, we add a new component to the ensemble to drive our empirical risk down in our ensemble. And greedy means we never kind of take that decision back, and we just go on and add more components until we have sufficiently reduced our empirical risk. Now, and in gradient boosting, we do that by using this nice concept of pseudo-residuals and so on. Not explain this here. Shouldn't even start, otherwise the video will be an extra hour long. The major change that we do in model-based boosting, or some people also call this component-wise boosting, is to say, hey, maybe let's use quite restricted and simple base learners. So what do we normally use in gradient boosting? So in gradient boosting, we often use trees, and we often use shallow trees. So trees of depth, I don't know, 2, 3, 4 maybe. But if we use trees of depth 2, 3, or 4, there's already interactions are possible in the model, and the deeper we make the trees, the less interpretable the model is. If we would use only stumps in tree-based boosting, we would actually construct a GAM, and that would be interpretable. But often that's not enough, and then people tend to use these trees with higher interaction depth, and then the model really becomes potentially either very difficult or becomes impossible to really interpret that model nicely. Now, in model-based boosting, the idea is to use base learners, which usually in the simplest version, in the vanilla, or let's say in the fundamental version of model-based boosting, we use base learners which only act on one feature, and we use splines, as we have explained this before for a GAM model. What we don't do is we don't necessarily already assume that every feature is active in our model, but we just have these potential base learners with splines, maybe even with only linear functions, all defined on one individual feature. And we have these base learners as a pool, and then we use the boosting framework, so these boosting iterations, where in every iteration we now search for the best fitting member of that pool. We add that into our ensemble, and then we iterate and go on. And at the end, that means we will have not only created a model which is still a GAM, because the model structure will reach at the end will exactly look like this here, because in each iteration we are adding a univariate term only defined on one feature. So we'll get that nicely decomposable and interpretable structure at the end, where we can read off the feature effects, in a certain sense the PDP curves, but we also can make that model sparse. So we'll only select the features and the effects which have a positive contribution in terms of driving the risk of that model down. And this is basically model-based boosting in a nutshell. There's not much more actually to say about that. So if you've understood how gradient boosting works, this is really easy to understand. Not many people, I have the impression, know that model class, and it's a pretty nice compromise between, like I said, empirical risk minimization in machine learning that still uses that, and it's applicable to basically any loss function, and you're basically still performing something like coordinate descent in that space and driving that risk down pretty aggressively, but at the end you're ending up with an interpretable and controllable model structure. Now, these base learners that we are using, might be splines, for example. They are usually still linear in the sense that they are linear in their parameters, so we can still combine and merge base learners of the same type. So if I have a base learner here with a certain parameterization theta of one type, so maybe it's like completely linear, it's X transpose theta, or it's like a spline for a certain feature, and then I have another spline on the same feature, I can simply add up their parameterizations and treat this as a single effect on that feature. I can just merge them together, right? So how would that look like in a fitting procedure? So we start with our offset here, with our intercepts, and learn that from the data. And then we add in, for example, a base learner for the third feature in the first iteration. And then in the second iteration, maybe again, the same type of base learner is selected again on the third feature. And now we exactly do that merging here. So we just add up these two parameters, which gives us this guy here. And then in the next iteration, we now add for the first time a different feature. So now we add in a base learner defined on feature 1. And at the end, we arrive at this structure here. Yeah? So we have this blue guy here, which is actually a mixture, or it's a mixture between these first two base learners which were selected, and then this last guy here, which was our base learner on the first feature. And we can now nicely read off the effect curves as in a generalized additive model. To make this a little bit more explicit, we'll now run through two examples. So one is extremely simple. So here we will boost together strictly linear models. So now I really in model-based boosting, all of our base learners are linear in their parameters, so we can do exactly that structure exploiting trick that I just showed. But here for this example, I will use even simpler base functions. I will use strictly linear base functions, which are also linear in the features. So I'll use functions like this, okay? So coefficient times feature value plus intercept term. So obviously, if I boost together a model from these components, so a strictly linear term plus another strictly linear term plus another strictly linear term, what model class can I generate with this? Pretty obviously, strictly linear models, nothing more. So in a certain sense, why am I doing that? Well, might be educational to look at that as an example, but we'll also see that, well, I guess I've already explained that, so I can say it right now. So if we now run this iterative procedure in model-based boosting, we can early stop that, right? Just we can stop that if the risk is not reduced anymore and we get feature selection for our linear model. So we can produce a sparse one. So first of all, let's simply run our model-based boosting with these strictly linear base learners here completely until convergence. So here we have run this again on the bike rental data set for about 1,000 iterations. And you can check that this converges to the of a linear model on the same data set. And we've also plotted here the relative frequencies of how often these base learners have been selected across the iterations. But I guess this is like more a technical thing. Obviously, this also depends on the step length here, on this new parameter, right? The smaller I make that, the more often I have to select a certain base learner across all iterations to completely model the effect that I would have in a normal linear model. But yeah, I guess I'll keep it at that here. What you can now do, you can now use component-wise boosting at the very least for feature selection to make your model sparse. And there are quite a few people who are using component-wise boosting exactly for that purpose, even with these strictly linear base learners. So you can early stop that. So here in that case here, all of our features that we used from the data set had a non-zero coefficient at the end. Here, when we early stop that after 20 iterations, and you can obviously also do this on risk, so in a smart fashion, by peeking at the risk either in bag or out of bag, you can see that some of these features have not been selected. So here we selected not the humidity and not the wind speed. So apparently these features were not useful. They were never selected in the component-wise boosting iterations to drive the risk down. So what else can we do? We can also interpret feature importances. So we can, even for the selected features, we can now additionally compute feature importance values. And we usually do this by aggregating the change in risk in each iteration where we have selected the feature. So if we are in a certain iteration, we select a feature, we just monitor how much our risk is reduced by adding in that feature. And then we do that, we check all iterations in which that feature has been selected, and we simply add up and aggregate all of these risk reductions, take them at the end as a mean value, and potentially present that in a table or in a little plot like here. So you can do that in bag, you can also do that out of bag. Usually if you run model-based boosting, you have like a validation set, which you also use to construct this optimal early stopping point. So you can either compute that risk reduction on the training set itself or on this validation set in a less biased fashion, which guards you a bit more against overfitting. And you can see what happens after 1,000 iterations and 20 iterations. And you can see here these risk reductions for these individual features, and you can then use them to associate feature importance values for the selected features, for the selected features in your model. You can also do this in a nonlinear fashion. So again, we'll do this here in an example on the bike rental data set. You can now use linear base learners, and you can use so-called centered splines to model nonlinear effects for our features. So we have to use certain variants of splines, so we have to center them to kind of ensure a fair selection between the linear parts and the nonlinear parts. I don't want to also go into the details here, to ensure that not like in each iteration the more flexible base learner is selected Yeah, you have to also use specific base learners for categoricals and so on, but all of this is possible and works. And our feature effect curves will now look like that. Here, yeah. Well, can use now splines to model them. You get your flexible model in the end with at least non-linear effect curves for each feature. You get a sparse model. You can see which features have been selected and which were apparently not very useful. So hopefully from even in a high dimensional data set, at the end you get a sparse model with hopefully only a handful of features selected, or at least a much smaller one than in the initial pool. And again, in the same fashion as before, we can aggregate the risk reduction for each feature across all of the iterations and then compute feature importance values from that. And if you do that, if you do this non-linear version of component-wise boosting, you get this sparse GAM structure at the end. Yeah? So you get nonlinear effects. You get a feature selection procedure baked into the algorithm. So you could say embedded feature selection. You get these feature importance values, and you get your feature effect curves that you can directly plot and visualize. And in a certain sense, if that model works well for your current data set, maybe you can forget about many of the other techniques that we are teaching here in this course. So before you kind of directly go from a linear model or a simple tree or a simple rule-based model to something that's completely non-parametric and non-linear and difficult and uninterpretable, like a super large ensemble or a deep neural network or a gradient boosting model with, I don't know, medium-sized trees, try out a model like this, which is somewhere in the middle, because that might actually give you a very good compromise and guard you against the pain at the end, guard you against the pain when combining these newer IML techniques with these pretty complicated nonlinear model classes where you then have to validate and so on, that you are allowed to do that, nothing goes wrong, you don't extract misleading information and so on. I guess I'm now repeating myself here. Interpretability is baked into the process, but you can still do nice empirical risk minimization and have nonlinear effects. So this concludes the session here. Thank you. Bye-bye.